So let's start by unraveling the basics of a Y connection. Have you ever looked up at a power pole and wondered how all those wires work together? Many of them use a special setup called a Y connection, which looks like the letter Y. It's actually one of the most common ways to connect three-phase electrical systems, which are, the backbone of our power grid. Think of a three-phase system as having three separate sources of electricity, or windings. In a Y connection, we take one end from each of these three windings and join them all together at a single central point. This special meeting place is called the neutral point. It's the heart of the Y configuration and is incredibly important for how the system functions, providing a common reference for all three phases. Let's visualize how this looks on a diagram. Imagine drawing three lines that all meet in the middle, just like the letter Y. Each of the three arms of the Y represents one of the system's windings. The other end of each winding, the one not connected to the center, is where we attach our main power lines. These are often labeled as line 1, L1, line 2, L2, and line 3, L3. These three lines are what carry the electrical power out from the source, like a transformer, to our homes and businesses. The central point where they all meet is connected to a fourth wire, which we call the neutral wire. This setup gives us a four-wire system, three hot lines, and one neutral. The neutral point is the secret ingredient that makes the Y connection so versatile. Because it's connected to all three phases, it acts as a stable reference. In a perfectly balanced system, where each phase is doing the exact same amount of work, very little current actually flows through this neutral wire. However, the real world is rarely perfect. If the loads on the different phases are unequal, the neutral wire provides a safe path for the unbalanced current to return to the source. This helps keep the voltages across each phase stable and prevents potential damage to connected equipment, making the whole system more reliable and safe for everyday use. So, to put it all together, the Y connection is a fundamental method for organizing three-phase power. It involves connecting three electrical windings to a common neutral point, creating a star-like shape. From the other ends of these windings, we run three power lines, L1, L2, L3, and a fourth neutral wire. This simple yet clever arrangement forms the basis for much of our modern electrical distribution network. It's a design that offers a great balance of efficiency, safety, and flexibility, which is why engineers rely on it so heavily to power our world, from giant industrial motors to the lights in our living rooms. It's a foundational concept in understanding how electricity gets from the power plant to you. Now that we understand the basic shape, let's talk about the electricity flowing through it. In a Y system, we actually have two different types of voltage to consider: phase voltage and line voltage. Phase voltage is the electrical pressure measured from any one of the main lines, like L1, to the central neutral point. It represents the voltage across a single winding. Line voltage, on the other hand, is the voltage measured between any two of the main lines, for example, from L1 to L2. Because the phases are offset from each other, the line voltage is always higher than the phase voltage. In a balanced Y system, the line voltage is precisely 1.732, the square root of 3, times the phase voltage. This relationship between line and phase voltage is a key characteristic of the Y connection. For example, if the phase voltage in a system is 277 volts, the line voltage would be 277 multiplied by 1.732, which equals approximately 480 volts. This is a very common voltage combination used in commercial buildings in the United States. This mathematical link is super handy for engineers because it allows them to design systems with multiple voltage options available from a single source. It's a simple rule. Line voltage equals phase voltage times the square root of 3. This predictable relationship makes calculations and system design much more straightforward and reliable for everyone involved. When it comes to current, things are much simpler. In a Y connection, the current that flows through any one of the main lines is exactly the same as the current flowing through its corresponding phase winding. This is because there is only one path for the current to take from the winding to the line. So, if you measure the current in line 1, it will be identical to the current in phase 1. This makes monitoring and calculating current loads very easy. Unlike voltage, there's no complex multiplier to remember. We can just say that line current equals phase current. This direct one-to-one relationship simplifies the process of protecting the system with fuses or circuit breakers. So, how do we calculate the total power in a balanced Y system? Power is the rate at which electrical energy is used, and we can figure it out using a straightforward formula. The total three-phase power is equal to the square root of 3 multiplied by the line voltage multiplied by the line current. The formula looks like this. Power equals the square root of 3 times line voltage times line current. This simple equation lets us calculate the total power delivered by all 3 phases combined. It's an essential tool for engineers to ensure that transformers, generators, and wires are correctly sized for the job they need to do, preventing overloads and ensuring efficient operation. Section 3. The pros and cons. Why we use the Y connection. One of the biggest advantages of the Y connection is how easy it is to ground the system. The neutral point provides a perfect single point to connect to the earth. Grounding is a critical safety feature in any electrical system. It helps to stabilize the voltage and provides a safe path for fault currents to flow in case of a problem, like a short circuit. This can prevent dangerous electric shocks and protect equipment from damage. This ability to create a solidly grounded neutral is one of the primary reasons why Y connections are so widely used in distribution networks that supply power directly to consumers. Safety always comes first, and a grounded Y helps ensure it. Another fantastic benefit is the ability to power different types of loads from one source. Remember how we have both line voltage and phase voltage? The higher line-to-line voltage, like 480 volts, is perfect for running large, powerful three-phase motors in factories. At the same time, the lower line-to-neutral phase voltage, like 277 volts, can be used to power single-phase loads like lighting, computers, and other smaller appliances. This dual voltage capability makes the Y connection incredibly flexible and cost-effective, especially in commercial and industrial buildings where you have a mix of heavy machinery and standard office equipment. It's like getting 2 systems in one. The Y connection also places less electrical stress on the individual windings of a transformer or generator. Because the voltage across each phase winding, the phase voltage, is lower than the line voltage, the insulation required for each winding doesn't need to be as robust. For a given line voltage, a Y-connected machine will have a phase voltage that is only about 58%, 1 divided by the square root of 3 of that value. This can make transformers and motors cheaper to manufacture and potentially more reliable over their lifespan. It's a subtle but important engineering detail that contributes to the overall efficiency and economics of our power grid, especially for long-distance power transmission. Of course, no system is perfect, and the Y connection has a couple of disadvantages. A major one is its reliance on the neutral wire. If the neutral connection is lost or broken, the system can become very unstable, especially if the loads are unbalanced. Without the neutral to keep things in check, the phase voltages can fluctuate wildly, with some becoming dangerously high and others dropping too low. This can easily damage or destroy sensitive electronic equipment. Another drawback is simply the need for a 4th wire. In some applications, like long-distance transmission lines, the cost of an extra conductor can add up, making a 3-wire system more economical. Section 4. Y in the wild real-world applications. If you want to see a Y connection in action, you don't have to look far. Just step outside and look up at the utility poles that line our streets. The power distribution systems that bring electricity to our neighborhoods almost always use a 4-wire Y connection. You'll typically see 3 main power lines running along the top of the pole and a 4th lower neutral wire. This setup allows the utility company to deliver high-voltage power efficiently over distances, and then easily tap into it to provide the single-phase power that our homes use. It's the standard for residential and commercial power distribution because of its safety and flexibility. Transformers are another place where Y connections are essential. A transformer is a device that changes the voltage of electricity up or down, and its internal coils, or windings, can be connected in several ways. The Y connection is a very popular choice for these windings. Sometimes only the secondary low-voltage side of a transformer is connected in a Y configuration to provide a neutral point for local distribution. In other cases, such as in large power substations. Both the primary, high voltage, and secondary windings might be connected in a Y, creating what is known as a Y-Y transformer. This is common in high voltage transmission systems. The reason Y connections are so common in transformers serving our homes and businesses is that they provide that crucial neutral point. When a transformer steps down voltage for residential use, the Y secondary gives us two different voltages. For instance, it provides the 120 volts needed for our wall outlets, measured from one line to neutral, and also the 208 or 240 volts needed for larger appliances like ovens and dryers, measured between two lines. This dual voltage capability, originating from a single transformer, is what makes the Y connection the go-to choice for final power distribution, making it both practical and efficient for our daily needs. From the massive generators at power plants to the final transformer on your street, the Y connection is a fundamental building block of our electrical world. It's used in power transmission to safely move electricity over long distances and in local distribution to provide the flexible, multi-voltage power required by everything from industrial factories to our homes. Its combination of a stable, groundable, neutral dual voltage outputs and relatively simple current characteristics makes it a reliable and versatile workhorse. So next time you flip a light switch, you can appreciate the clever engineering of the Y connection working silently behind the scenes to power your world.